So we have a calorimeter problem. We're going to have 10 milliliters of 1 molar AgNO3 solution added to 10 milliliters of 1 molar NaCl solution at 25 degrees Celsius in a calorimeter. My handwriting is terrible, so disregard that. Hopefully it gets better. A precipitate forms and the temperature increases to 32.6 degrees Celsius. Now they tell us the specific heat of the aqueous mixture is 4.18 joules per gram degree Celsius. And they also tell us the density of the mixture is 1 gram per milliliter. And we don't have to, they make it a little more simple. The calorimeter absorbs a negligible amount of heat. So what they want is to find delta H in kilojoules for the precipitation reaction, which is right over here. Okay, so where are we going to start with this? There's a lot of information here, and what I like to do to start is to kind of write down the information, see what you're looking at, and then go from there. And also any useful equations that you know of. And since this is a calorimeter problem, we're going to look at Q is equal to S M delta T, where S is the specific heat of the solution, M is the total mass, and our change in temperature. And this is really the only one we need to look at because the calorimeter absorbs a negligible amount of heat. If it didn't, you might also have to take into account the calorimeter's heat capacity, and you're going to have another Q in here, which is going to have that heat capacity, which is not the specific heat capacity, and you're going to have to account for that other heat. We won't have to do this one. Get a different color here. That one we're not doing because the calorimeter is not going to be a source of heat in this equation, in this problem. It's not going to be a source where heat's going to go to. This is one we do need to look at. And it's also important to point out this calorimeter, this C here, is different than this S. So the heat capacity C, this guy, I mean that's specific to an object. You know what that is. It's going to be an experimentally determined value that they're going to give you in the problem. S over here, that is the specific heat capacity. It's the energy needed to raise 1 gram of that substance by 1 degree Celsius. We do have that here. And if you kind of get confused between these two, and if your problem does require you to use both of these, and I'll probably put a problem up like that here in a little bit that does require both of these, it's kind of still simple to see which one goes where because your units will cancel. And we'll kind of see that later on. So where do we start here? So we have 10 milliliters of 1 molar AgNO3. And they're nice enough to tell us the density. Let's go ahead and write our S value down here since we know it. 4.18 joules per gram degree Celsius. Again, that's just how much energy does it take to raise it 1 gram. To raise 1 gram 1 degree. Sorry, said that wrong. Okay, so we have our specific heat. Let's look at our mass. That's something that they don't just outright give us, but we have everything that we need to find it. So we have 10 milliliters of AgNO3, and we have 10 milliliters of NaCl. So we have a total of 20 milliliters. And they tell us that the density for the mixture of the solution is 1 gram per milliliter. So we're going to cancel our units here. Put a 1 there. Milliliters will cancel. Make that look like a capital L. And that's going to leave us with 20 grams for our mass. That's going to go this 20 is going to go pretty simple to solve for that. It's not outwardly just shown in the question, but it's easy enough to find. The next thing we have to look at, delta T. And what does delta T mean? It's a change in temperature. And you can, in most cases, think of that as final minus initial. So we also have that. We can solve for that pretty easy. Let me change the way I put that. Delta T is equal to the final temperature, which we have is 32.6 degrees Celsius. Minus our initial 25 degrees Celsius. And you may notice I'm kind of being terrible with sig figs. They actually did write this as 10.0 milliliters, 1.00 molarity here. We won't worry too much about sig figs for this. 5, 6, 7, so we have 7.6, I think is going to be our delta T. That's how much it's changed by. So now we have delta T, we have the mass, we know the specific heat because they gave it to us. We can solve for Q. Q is going to be equal to 4.18 joules per gram degree Celsius. Multiplied by our 20 grams multiplied by our change in temperature. Now, we kind of mentioned before between these two equations, the one we're not using and this one, that you could kind of tell what needed to go where based off of units canceling. If this joules per gram degree Celsius was in this problem over here, all you have is temperature. All you would cancel is degrees Celsius. You would still be left with joules per gram. But Q is going to give you units of joules in this instance. So we'll see here, grams cancels with grams. Degrees Celsius, it's in the denominator. Same thing here, this would be technically numerator. That's in the denominator over here. Cancels, degrees Celsius is going to cancel. We're left with just joules. And if we put that into our calculator, we should get something that looks like 6.4 times 10. Oops. To the second power joules for our units. And some people stop here. They say this is my heat, this is my joules, I'm done. But remember, the question wants to know calculate delta H in kilojoules for the precipitation reaction. And so we have a different number of moles. We don't have 1 mole of everything up here. The reaction is stated as such, and so we can use that to solve for it. But I need to use how many moles I have. And fortunately, it's implicitly in here, but this is a 1 mole to 1 mole to 1 mole. So it's a 1 to 1 across here. So I could use either Ag plus or Cl minus here, but I'm just going to use Ag plus to figure out how many moles of AgCl solid we have. And my handwriting's terrible. This is actually aqueous, and that's aqueous. That's what those are for. So we have moles of Ag plus, silver ions there. And that's going to be equal to our 10 milliliters multiplied by, it's a 1 molar quantity. And you may have to refer back. This is going to be 1 mole per liter. That's what that means. So we have 1 mole per, Now I can't write 1 liter because I'm in milliliters here. A lot of times I get asked, does it need to be in milliliters or liters, or in thermodynamics, joules or kilojoules? It just has to all be the same throughout your entire problem. So we're in milliliters here, so we're going to put milliliters here. If this was in liters, this could be 1. This is in milliliters, so this is going to be in milliliters. 1,000 milliliters is equal to 1 liter. 1 liter is equal to 1,000 milliliters. So we run that through and we get 1.00 times 10 to the negative 2 moles of Ag plus. Silver ions there. Okay? That's going to be equal to moles of AgCl, because this balanced equation up here, it's a 1-to-1. For every mole of this, we have 1 mole of that. So now we know moles of our AgCl. So our delta H, which is going to be in, oops, did that backwards? Kilojoules per mole .4 times 10 to the second joules, I haven't switched yet, over 1 times 10 to the negative 2 moles AgCl. At this step, you can just divide by 1,000 here. Same thing with liters. You have, between the milliliters and liters, you have 1,000 joules per 1 kilojoule. It's super sloppy. So once you've done all that, what's it going to give you? Well, you're going to have 64 kilojoules per mole. Now, one thing to keep in mind, because heat was evolved from this system by convention, this is going to be negative 64 kilojoules. Should probably add per mole AgCl just to be consistent. So hopefully that was helpful. I will probably put up a problem that uses both of these values here, both of these equations. And this was my first video, so hopefully they get better from here. But if you liked it, go ahead and actually like it, click like, subscribe, and hopefully we'll put up some more.